Hello everyone again. This is lecture number 3 for work, energy and power. In the previous discussion, we have completed the introduction, which was basically the scalar product of vectors, and second was about work energy theorem. In this, we will move forward with the concepts of third subtopic, that is work. So that thing being said, that I'm Samir Lawankar. This is lecture number 3 on work, energy and power. Let's begin our discussion. So currently we are on the third topic, that is work here. Before that, we have completed the first two topics, that is introduction and the notions of work and the kinetic energy, the work energy theorem. So before moving forward today, let me just iterate you a little bit, a quick revision of the topics which we have understood, and then we can move forward with the present discussion which we are working. Okay. So first of all, the initial introduction of this chapter started with the concept which is called as scalar product of vector multiplication. So it is nothing but called as your scalar. So first of all, we understood a concept which is scalar product of two vectors. What was this basically? The product of A dot B is nothing but equal to AB cos theta. Correct? And there were some properties related to it. So properties, some of the prominent properties were commutative law, that is A dot B is equal to B dot A. The second was A dot B plus C is equal to A dot B plus A dot C. And then things like I dot I is equal to J dot J is equal to K dot K is equal to 1. And I dot J equal to J dot K is equal to K dot I is equal to 0. Okay. And third thing, using all these properties, what we got, that let us say if A is nothing but equal to AX I cap plus AY J cap plus AZ K cap, and B is equal to BX I cap plus BY J cap plus BZ K cap, then what we can say that A dot B is nothing but equal to AX BX plus AY BY plus AZ BZ. Okay. Also A dot A is nothing but equal to magnitude of square of the magnitude, which is nothing but equal to AX square plus AY square plus AZ square. Okay. So I hope these things are clear. Then in the work energy theorem concepts, we understood that, first of all, we understood about kinetic energy, which was equal to half mv squared. Then we understood work, which is written as equal to nothing but F dot D. Then we understood the work energy theorem, which in mathematical form simply states that a change in kinetic energy is equal to work done by the external force. Okay. So that's a quick revision of everything which we have completed or understood in the last 2 lectures. Now let us start this third lecture with the basic discussions which we are doing about the work. Okay. So these all things are completed. In the previous discussion, we have completed these examples also to understand when and else can we say that the work done is 0. So either displacement can be 0. So F dot D. Fw is equal to F dot D, which is equal to F multiplied by D multiplied by cos theta. So either D is equal to 0 or F is equal to 0 or theta is 90 degrees. So in all these sequences here, what we can say that the work done is nothing but equal to 0. Work done is nothing but equal to 0. So that thing being said, now let us move forward with today's discussion. Okay, so we have completely did a quick revision also, and now we are understanding the further discussions. Okay, so it is written here that the work can be both positive also and negative also. If you remember correctly, we did a question regarding a raindrop, correct, in which it was being said that there is a resistive force and a gravitational force being acted upon. correct? If you remember correctly. And when we calculated the results, the total energy came out to be positive. The energy due to this gravitational force came out to be positive, but the energy due to this resistive force, not the energy, I'm really sorry, not the energy, the work done. The work done due to resistive force came out to be negative. Okay, so we have already seen an example in which the work done calculated was positive also and negative also. Okay, fine then. So work can be both positive and negative. So if the theta is between 0 and 90 degrees, cos theta is positive. Okay. If theta is between 90 degrees and 180 degrees, then cos theta is negative. Okay. So in the previous case scenario, what was happening? For resistive force, if you see clearly, this was your drop. The displacement of this drop was in this direction, correct? But the force acting was in this direction, right? So this was the F value, this was your D value, correct? So as 180 degree angle is being formed here, in mathematics you may have studied that what is cos 180 degree? It is nothing but equal to minus. Okay, so that is why that is why what we wrote here was that if the work done can be positive also and the work done can be negative also. Okay, so if theta is between 0 and 90 degrees, cos theta is positive, and if the theta is between 90 degrees and 180 degrees, then cos theta is negative. In many examples, the friction force opposes displacement and theta is 180 degrees. Okay, so you will understand this in subsequent classes also, and you will understand more about friction. So generally, let us say if the displacement is in this direction, then very many general sequences, the frictional force is being acted upon in this direction. The frictional force is acted upon in this direction. So what is the angle being made here? The angle of force and displacement is theta is equal to 180 degrees. Okay, so in many examples, the frictional force opposes displacement and theta is equal to 180 degrees. Then what is the work done? Work done by the friction is negative. How it is negative? Because cos 180 is negative. Hence, when you will write the work done is nothing but equal to magnitude of this frictional force multiplied by magnitude of this displacement multiplied by cos 180, which will give you minus. Okay. Next thing is, it is clear that the work and energy have the same dimensions. So you have understood the concept of dimensions in the first chapter, that is units and dimensions. So what is basically dimensions? We just need to multiply the basic units in terms of L, M and T and calculate the values of dimensions. Okay. So let us try to calculate this for the same sequence here. So what is basically work? Work is nothing but force into displacement into cos theta, correct? If you see clearly, what is the unit of force? Force is nothing but equal to kg meter per second square. What is distance? So distance has a unit which is equal to meter, correct? Cos theta has no units. Okay, so if we write the dimensions of W, it is nothing but equal to, in terms of L, in terms of MLT, MLT. So you can see clearly what is M here. M has a power 1. What is L here? L has a power 1 and 1 plus 1, which will give you 2. And what is time here? Time will give you minus 2. Hence, what is the dimension of work? Work has a dimension which is M1 L2 T minus 2. Okay, so I hope it is clear. You can understand how it is M1 L2 T minus 2. You will understand in subsequent classes work and energy, and we will understand about energy in the subsequent classes. For now, we are just referring here that work and energy both have the same dimensions, which is nothing but M L2 T minus 2. Okay, fine. So moving forward, the SI unit of this is joules. Okay, so please remember this. What is the SI unit of work? The SI unit of work is joules. So Joule was basically a prominent scientist on whose name the SI unit of work is being kept on. Okay, so SI unit of work is joules. So joules is written as G. Okay, so the SI unit of this is joules, named after the famous British physicist James Prescott Joule. Okay, fine. Now Since work and energy are so widely used as physical concepts, alternative units abound, and some of these are listed in the table. Okay, so generally, as we already know that, let us say if I take for length also, na, anything, all the things in this complete universe cannot be explained using the concept of meters, correct? Because some things are, let's suppose, in nanometers, you cannot write 0.000 up till 9 for everything, right? So that's why we distributed or made different ways of understanding this concept of work, correct? We said something to be kilometer, we said something to be hectometer, we said nanometer, so we created these different quantities. Okay, so in similar terms, because there was very variations in these quantities, we defined different units of work. So everything was so these units which are being written here are nothing but the multiplicative factors of the word joule. Okay, so I would suggest you to remember them, but they are not as much important. But as the days goes by, and you will understand concepts such as electrical charges, etc., these some of these things will be directly in your head directly. So don't be hesitant regarding this. You can even just I may suggest, and you can remember as electron volts and this kilowatt hour. Okay, fine. So here, so what are these basically? So what is erg? Erg is basically 10 to the power minus 7 joules. What is electron volts? It is 1.6 into 10 to the power minus 19 joules. Okay. What is calorie? Calorie is 4.186 joules. And what is kilowatt hour? Kilowatt hour is basically 3.6 into 10 to the power 6. Fine, we will understand about the kilowatt hour in the second part, means in the later stages of this lecture series. Okay, fine. So that thing being said, what is the conclusion of this part of the slide? So we understood first of all that work can be both positive and negative. The first thing, and second thing is, and we understood this. The dimensions is this, and the third thing is that the SI unit of this is. Okay. So that thing being said, let's move forward. Let us try to do one of the questions regarding these examples of work or regarding this concept of work. Okay, so a cyclist comes to a skidding stop in 10 meters. Let us understand what is being explained here actually. So let us say this was a cyclist, okay, and he was moving in this direction. Now, by some sense or another, he applied brakes. So when the brakes were being applied, if you see clearly, these tires were in a rotatory motion, correct? So when the brakes were being put apart, they were so good that the rotational motion of this was put to stop. But because there was a motion of this at a very higher stage, we know that there would be some amount of time required for this complete body to get to a complete stop. Therefore, what was happening is that without even rotation, due to the force or due to the energy which this complete body had, there was something which is called as skidding. Skidding took place. So basically, you will understand about skidding much more clearly in the chapter of rotation. Just to explain you in a very easy terms, what is basically happening? This part of tire is being moved from this location to this location without any rotation. But that is basically skidding is happening. Okay. Fine. So that is the basic understanding of skidding. We will understand more about skidding in the chapter of rotation. Okay. Fine. So a cyclist comes to a skidding stop in 10 meters. So basically we can understand it. Let us say this is your cycle. These are the two. Okay, I will make much more clear cycle. So let us say this is your cycle being kept here. Okay, and this is being moved. So the amount of displacement of this cycle when it comes to a complete stop is given as 10 meters. Okay. During this process, the force on the cycle due to the road. Please remember, please understand this line very, very carefully because that is the crux of this question. Okay. It is said that the force on the cycle due to the road is 200 meters and is directed opposed to the motion. Okay. So what is the force on the cycle? The force on the cycle is basically, if I make another free body diagram of this, so what is the force acting on this? The force acting is in this direction, which is 200 newtons. Okay. The question asked is how much work does the road do on the cycle? And second thing is how much work does the cycle do on the road? Let us go very slowly and understand both of these concepts here. So work done on the cycle. So please understand this. So work done on the cycle. Please understand. Work done is done on the cycle. So something is being done on this. Who is doing this work? The work done is done by the road. Is the work done by the stopping frictional force on the cycle due to road. So it is quite evident the road will only and only provide you the frictional force, right? So what is being done? The opposing motion is being applied due to road. So let us say road was some person who was trying to block you. Okay, so how was this blocking done? By a concept which is called as frictional. Okay. Therefore, what is the work done on the cycle by the road? Because it is a opposing force being done or opposing force is being utilized. Therefore, what we can say that the displacement was in this direction and an opposing force is acting upon in this direction. Okay. So just reading here. So the stopping force and the displacement makes an angle of 180 with each other. Therefore, what we can write? We can write simply work done is nothing but equal to this force multiplied by d into cos of 180 degrees. Force is given to you as 200, displacement is given to you as 10, this is nothing but minus 1, and this is nothing but equal to minus of 2000. We understood the units just before, which is nothing but joules. Okay, what is the question here? The work done on the cycle by the road is minus 2000 joules. Clear? Fine. Moving on. So it is the negative work that brings the cycle to a halt in accordance with the WE theorem. So quite evident because the force is being acted upon, the velocity is acted upon this direction. To decrease the velocity, you need to add a force in this direction only, then only you can stop. Okay, fine. Moving on, from the Newton's third law, an equal and opposite force acts on the road due to cycle. So in the laws of motion concept, you may have understood the concept of free body diagram. So let us suppose I make a free body diagram. So let us say that this was the cycle. Okay, so the force acting on this cycle can be said as like this. So let us say this is F frictional. Therefore, on the road, if I make the force on the road will be F frictional in this direction. Okay, so this was for cycle and this is for road. Okay. So from Newton's third law, an equal and opposite force acts on the road due to the cycle. What is its magnitude? Its magnitude is 200 newtons, is in this direction. However, the road undergoes no displacement. Very important line. The road is intact there only. There is no displacement of this road. Therefore, what is the work done? Work done is nothing but equal to F multiplied by D multiplied by cos 0. Which is nothing but equal to what is the work done? Sorry, what is the force? It's plus 200. Because the displacement is 0, it will be 0 multiplied by 1, which is equal to 0. Okay. Therefore, what is the work done on the cycle by the road? It is nothing but equal to minus 2000 joules. And what is the work done by the cycle on the road? It is equal to 0 joules. Okay. So you can understand this clearly that even though the forces are equal and opposite, the work done is not equal. Please remember this is a very important point to understand, to make you explain this example, that the force will be equal and opposite. So the Newton's third law is applicable to force, but the work done is not equal. Okay, so you may say that okay, so some work done is done by this frictional force on this, and hence there will be some opposite work done here also. So this is not the general case every time. Okay, so that is the only explanation or only reason which you need to understand from this question. Fine. That thing being said, let us understand. So only thing which I just uttered is written here. So the lesson of example X6.3, which was the previous one, is that though the force on a body A exerted by the body B is always equal and opposite to that on B by A, which is Newton's third law. So basically the force exerted by the cycle on the road is negative of the force exerted by road on the cycle. The work done on A by B is not necessarily equal and opposite to the work done on B by A. So that is the only explanation of the previous question. Okay, so it is just written here. Everything which I said is written here. Okay, so that's again revision is been done. Fine. So that thing being said, now we have completed the three basic subtopics of your chapter work, energy and power. We started with the scalar product, then we understood the kinetic energy theorem, then we understood the concept of work, we understood when can the work be zero, when it cannot be not. We understood that although the uh, the Newton's third law is valid for the forces, but it is not certain that it is valid for work done. Okay, so work done by the opposing forces need not be same always. Okay, right. So let's start with a new subtopic now. Let us understand more about the kinetic energy. Okay, so in the previous discussion, when we were understanding the concept of kinetic energy theorem, we understood that what is basically called as kinetic energy. So half multiplied by mass multiplied by square of this velocity is called as your kinetic energy. Okay, so let us understand more about kinetic energy. So as noted earlier, if an object of mass m, let us suppose this is some mass m having a velocity v, let us say this has some velocity v, then its kinetic energy k is denoted as, so k is basically equal to half m v square. Okay. Next thing, kinetic energy is scalar quantity, quite evident. Why is kinetic energy a scalar quantity? Because it is nothing but a scalar product. As you can see, it is a scalar product of v dot v, and because half is also scalar, m is also scalar, and here this is v square is nothing but the magnitude of v dot v or magnitude of vector v, and hence this is also a scalar. Therefore, this complete kinetic energy is a scalar quantity. Fine. So that is the explanation of this. Okay. Moving on, the kinetic energy of an object is a measure of the work an object can do by the virtue of its motion. Please understand the definition very clearly. So what is basically kinetic energy? Kinetic energy of an object is a measure of the work. So it's used to calculate the work only, but how is it calculating the work? It is calculating the measure of the work which that object can do by the virtue of its motion. So when an object or a particle is moving in some direction with some velocity v, that is how it can capture the work done by it. Okay, so due to its motion, whatever the energy is being interacted upon or whatever the work is being done upon can be calculated using the formula or using the concept of kinetic energy. Okay, fine. That thing being said, this notion has been intuitively known for a long time. The kinetic energy of a fast flowing stream has been used to grind corn. Okay, sailing ships employ the kinetic energy of the wind. Table lists the kinetic energies of various objects. So some of the kinetic energies have been given here. So if you look at this very carefully, what is the general thing which is happening here? For a car, the mass is given, speed is given. So how will you calculate the kinetic energy? It is nothing but half into 2000 into 25 squared. Correct? Similarly, for an air molecule, how will you calculate? So it is nothing but kinetic energy, which is equal to half into 10 to the power minus 26 into 500. So that is how you can calculate these kinetic energies. Don't need to remember any of this sort. It is just for your reference purposes, so as to see that what is the variation of kinetic energy generally observed in our surroundings. So then for a simple reason such as car, you can observe here that it is going till 10 to the power 5. Okay, and for reasons such as 10 to the power, as you can see for the air molecule, it is going for 10 to the power minus 21 also. It is going for 6.3 10 to the power 5 also. It is going to 10 to the power minus 21 also. So that was a basic thing which I need to explain to you. So you can see the variation. So it's going from 10 to the power 5 and then keep on decreasing and going to 10 to the power minus 21 also. Okay. Fine. So that thing being said, now let us understand another example which is based upon your kinetic energy concept. So in ballistics demonstration, a police officer fires a bullet. So let us say that this is a bullet here and it is being fired. Okay. The mass of this bullet is given. So M is given to you as 50 grams. Okay. M is given to as 50 grams. What is 50 grams in kgs? So it's nothing but 50 into 10 to the power minus 3 kgs. The speed is given to you. So velocity is nothing but equal to 200 meter per second on soft plywood. So there was a soft plywood being kept here. Let us suppose a soft plywood was being kept here. The thickness is given to you as 2 centimeters. If I convert it 2 centimeter into meters, it is nothing but 2 into 10 to the power minus 2 meters. Okay. The bullet emerges with only 10% of its initial kinetic energy. So after this, let us say there was a hole here. After means it was initially it was completely blank, but afterwards, due to the moving of this bullet through this soft plywood, there was a hole, and the bullet which is in present here has a kinetic energy, which is kinetic energy final, which is nothing but equal to 10% of its initial kinetic energy. That is 0.1 into kinetic energy initial. So it is given in the question that the bullet emerges with only 10% of its initial kinetic energy. Okay. So the question asks is, what is the emergent speed of the bullet? Emergent speed as in, what is the final velocity at this location? Okay. So these are given to in the question. Now let us try to understand the question, solve the question. Okay. Fine. So first of all, let us calculate the initial kinetic energy. So initial kinetic energy is nothing but equal to half into m into vi squared. Everything is given to you in the question. It is nothing but half into 50 into 10 to the power minus 3 into 200 squared. Correct? So when you will calculate it, you will get the answer as equal to 1000 joules. Okay, so this is the initial kinetic energy calculated. Okay. Now it is given in the question that the final kinetic energy is nothing but 10% of initial kinetic energy. So therefore we can say that kinetic energy final is nothing but equal to 10%, that can be 10 by 100 of 1000. That is initial kinetic energy. So this is nothing but equal to 100 joules. Okay, so now we have the kinetic energy of final kinetic energy. We know the mass, we just need to calculate the velocity. How will we calculate the velocity? We know again, we will apply kinetic energy final, which is nothing but equal to half into mass will be same into final velocity squared. Correct? So what is final velocity? Final velocity will be nothing but equal to root over 2 into kinetic energy final upon mass. Correct? That is nothing but equal to under root of 2 into what is kinetic energy final, which is 100 upon what is mass. Mass will be 50 into 10 to the power minus 3. Okay, please take out the units very clearly, because change in units can make a blunder in the calculations. Okay, therefore final value of velocity will be nothing but equal to, just calculate it, you will get the answer as 63.2 meter per second. Okay, so that thing being said, now let us understand. So what is the final conclusion here? The final conclusion here is the speed is reduced by approximately 68% and not 90%. So one may say the kinetic energy is reduced to 10%. That means the velocity will also reduce to 10%. But in the actual case, the velocity V final is not equal to 10% of Vi. It is only approximately reduced to 68%. Okay. So that is one more conclusion here. Okay. So that is the ending of this part of the subtopic also. So till now we have understood first of all about scalar product, then we understood about the kinetic energy theorem, then we understood about work done, and now we also understood about kinetic energy. Okay, so in these concepts, when we were understanding the kinetic energy theorem, the work done, and the kinetic energy, we understood each and every statement with assumption. We can say an assumption, or we can say a case in which the force was understood as constant. F is constant. Okay, now let us broaden our aspects and understand what happens when this F value is not constant. Okay, let us try to understand that what happens when this value of F is not constant. So let us start a new subtopic now, that is work done by a variable force. Okay, so work done by a variable force. So what happens, or let us understand what is happening when the work done, what is the value of the work done by a variable force. Okay, The constant force is there, quite evident. Every time there cannot be a solution when the force is constant. It is the variable force which is more commonly encountered. Which is more commonly encountered simply means that generally in real life scenarios, in our day-to-day life, we generally encounter with a variable force. Okay. The given figure is a plot of varying force in one dimension. So what is the simply meaning of this? That is, as we keep on changing with the space, the amount of force which is acting upon it is changing. Okay. So let's say we were at displacement xi. We went to this location, let's say x2, or went to this location x3. The amount of forces which were acting at these locations were not constant, they were some different values. Okay. So this was basically how can we understand this situation again. Let us say this is some object with a mass m, and let us say this is some force which is being acted upon it. Okay. So let us say this is moving from this location to this location. If I divide this into several divisions, let's say this is to be x0, this is x1, this is x2, this is x3, this is x4, this is x5, this is x6. Okay. So variable force simply means that for each value of this x0, x1, x2, x3, then dot till x4, x5, x6, we have different values of force. So f of x0 will be used here, f of x1 will be used here, f of x2 will be used here, f of x3 will be used, and similarly case scenario for 4, 5 and 6 also. So that is the simple meaning that with a change in displacement, the value of the force is also changed. Okay, so that is the simple meaning if you try to understand this for one dimension. Okay, the given figure is a plot of varying force in one dimension. If the displacement delta x is small, now we are trying to understand this concept using very small values of, so basically differential calculus is being involved here. Okay, so now if the displacement delta x is very small, so let us say that the displacement is only very small, which is approximately delta x. Okay, which is equal to delta x, then what we can say that this force f of x can be taken as approximately constant, because in that very small amount of displacement, this f of x won't vary much. So we can say, or we can assume it to be approximately constant. If it is assumed as approximately constant, what we can say that the change in work, or not a change in work, or the work done during that small displacement delta x, what will be its value? Its value will be nothing but equal to f of x into delta x. Correct? So it's f of x into delta x. This is illustrated in figure A. So I think so this is only your figure A, in which it has been explained that for very small values. So if I just look at this very small delta x, then for this we can directly say that work done is nothing but f of x into delta x. Or in another term, what we can say that it is nothing but this small area. This small area is nothing but the work done in that very small displacement delta x. Fine. So we got this concept first of all. Now let us move with this concept. So this illustrated in figure A. Now if we add successive rectangular areas, okay, so we keep on adding some delta x, let's say this delta x, this delta x, this delta x, this delta x, okay. So basically it is nothing but the area addition of all of these different displacements. Correct? So this can be written as nothing but, so we can write it as summation of what? Summation of force which is varying with x into this displacement delta x. From where to where? We will start with xi, we will end at x. Okay, so that is how the representation of summation is being explained. So what we need to sum? We need to sum f of x into delta x, so that we can get the complete work. And from where to where we will understand, or where to where we will sum it. We will start with from xi and we will sum it till x. Okay, so therefore the total work done is nothing but equal to summation of, is approximately equal to summation of xi to xi fx delta x. Okay, so where the summation is done from the initial position xi to the final position x. Okay, so we understood so we have understood the introductory concept of how we are trying to find out the work done by the variable force. Okay, fine. Let us move forward now. So now if the displacement is approached very, very zero, so now what we're basically doing, so basically first of all we had some value of delta x like this. Let us say we decrease this, we go till here, we go or very more, and then some at one location it will come a quantity which is very, very small. Okay, so that small quantity is basically can be written as nothing but when delta x is approximately equal to 0 or delta x tends to 0. Okay, so now if the displacements are allowed to approach 0, so if the displacements are allowed to approach 0, then the number of terms in sum increases without limit. Okay, what is being written here? As the displacement allowed to approach 0, the number of terms in the sum increases without limit. Basically, there will be a large number of additions which we need to do if we perform this addition, which has been explained in the next slide, by this summation usage. But the sum approaches a definite value. But the sum will be a definite value, but it would require a large number of additions to be done. So what is this complete value? This value is nothing but the area under the curve, which is explained in figure B. So how can we write this representation? We can just write this representation as nothing but this work done is nothing but limit delta x tends to 0 f of x delta x. Correct? Now if we need to do this sum from xi to xf, we can write this is similar in the form of integral sign. Correct? So it is nothing but integration of f of x dx. Hope it is clear to you. So again, the units or the limit should be from xi to x. Fine. So that is how we can find the work done. So work done is basically nothing but integration of xi to xf fx dx. Okay. Where limit stands for the limit of the sum, where delta x tends to 0. Thus for a varying force, the work done can be expressed as a definite integral. Explaining again, thus for a varying force, the work done can be expressed as a definite integral. Of force over displacement. So I hope you can understand every word which has been uttered here is nothing but explaining this equation, that is W is nothing but equal to integral xi to xf fx dx. Okay. So you will understand this and much more in mathematics about definite and indefinite integral. So if I just integrate it like this, let's say I denote something and I integrate it like this, this is called as an indefinite integral. And if I denote something like this, dx from let's say xi to xf, and this is called as your definite integral. Okay, so I hope you understood this concept also. So you will understand more about this in mathematics. Okay, so whenever we find the final answer for this, we need to add a plus c constant here. Okay, and here this plus c is omitted, so there is no use of plus c here. Okay, so these are the only small basic properties of indefinite integral and definite integral. So basic usages only, we just need to understand here that W is can be said as for a variable. It is nothing but integration of xi to xf fx. Okay. Okay, so now let us try to use this complete concept in one of the examples so that we can understand this complete discussion. Okay, so look at the question. Let's read the question and then we can move forward. So a woman pushes a trunk on a railway platform which has a rough surface. Okay, so let us say this is a rough surface. There was a woman here and she was pushing a trunk. Let us suppose this is a trunk. Okay, and the woman is pushing. She applies a force of 100 newtons over a distance of 10 meters. So what was the force initially? The force initially was 100 newtons. And what was the displacement being made? The displacement made was 10 meters. Okay. Thereafter, she gets progressively tired and her applied force reduces linearly with distance to 50 meters. Okay. The total distance the trunk has been moved is 20 meters. Okay, so let us stop till here only and let us try to understand the plot first. Okay, so please look at this location clearly. So what was written there, that what did the movement do? Till 10 meter displacement, she applied a constant force which was equal to 100 meters. So this was the constant force of 100 newtons being applied. After this, she got tired, and then till displacement of next 10 meters, because it is written the total displacement 20 meters. That means that for the next 10 meters, the force reduced linearly. As it was reduced linearly, we will draw a straight line and we will end it at 50 newtons. Okay, so I hope it is clear. You can understand what the basic crux which has been explained till this point here. So I hope you understand everything which is written till this point here. Now let us move forward. The next point says that plot the force applied by the woman and the frictional force, which is 50 newtons versus displacement. So what it is saying, that there is an additional force F, which is 50 minus, it is 50 also. Okay, frictional force will be in the negative sense. Okay, so how we are trying to plot this? So this force capital F was first of all 100, then it went to this direction. Right, so this is how we can draw the force for x is equal to 0 to x equal to 20 meters, and the constant value of frictional force, which is minus 50. Why? Because it is in the negative direction, with the displacement which is in positive direction. So I hope the diagram is clear to you. So plot the force applied by the woman and the frictional force, which is 50 newtons versus displacement. So we drew the force versus displacement. You can see clearly that this is a variable force, right? So with the change in displacement, the force is changing. Now the question is asked, calculate the work done by the two forces over 20 meters. Okay, so let us first calculate the work done due to this forces. In the previous discussion only, we have understood the topic, that what is the work done? The work done by a variable force is nothing but equal to area under the curve for the required or for the displacement completed, correct? So it is nothing but the area under the curve for the displacement completed. So now let us try to find the same for the work done due to this capital force F. Okay, so as you can see clearly, what is the complete area? So it is nothing but this area plus this area, correct? So let me just write. So what will be the area? So it's work done due to force, which is nothing but area of rectangle A, B, C, D plus area of rectangle, not a rectangle, it's a trapezium now, area of trapezium CDIE, let us suppose. Okay, fine. So let us calculate the area of rectangle ABCD. How will we calculate? It is nothing but equal to your value of 100, multiplied by 10, correct? So this is nothing but 100 multiplied by 10. What is a trapezium? It is, we know what is the area of trapezium. It is half into sum of parallel sides into height. So what is sum of parallel sides? It is nothing but, what is this height? It is 50, correct? What is this height? This is 100. And what is this height? Or what is the distance here? It is 20 minus 10, which is equal to 10. Okay, so this will give you 1000, and this will give you, if I'm not wrong, it's 150 into 5. So 155 is, I think, 750. Therefore, the final answer which you will get is nothing but 1000 plus 750, which is equal to 1750 joules. Okay, so what is the conclusion of this? So even if there's a variable force, you can calculate the work done by this force. So here the work done by the force will be nothing but equal to the area of the rectangle ABCD plus the area of the trapezium CDIE. Okay, so how will we do it? We just did area of this rectangle plus the area of this trapezium, correct? Please remember, we will only do till this, even though there is a frictional force acting here. So we won't add this into the area of the force which is due to capital F. Okay, so capital F will be only to this face till 0 only, correct? So don't do any confusion regarding that. Okay, even though there is a force being interacted here due to some another force, we won't add it into our scenario of capital F. Okay, so therefore we got that the work done due to force capital F is nothing but equal to 1750 joules. Okay, fine. So this thing is explained. Now let us find out the the work due to frictional force. Okay, let me just rub this. Okay, so the work done by the frictional force is nothing but again equal to area of the curve, which is nothing but here A G H I. So it's a rectangle, simple rectangle. So what you will do, you will just do simply minus 50 multiplied by 20. So it is nothing but minus 1000 joules. Okay, so that is how you can find the area of the curve, or basically the work done by the frictional force. Okay, so work done by the frictional force, as it is written here also, that the work done by the frictional force nothing but BF, which is nothing but the area of the rectangle AGHI. So that is equal to nothing but WF, which is equal to minus 50 to 20. That's minus 50 into this is your 20. This is your minus 50. This is your 20. Therefore, this is the area which you need to calculate, which is equal to minus 1000 joules. Okay. Therefore, the area of the negative side of the force axis has a negative sign. It's quite evident. So nothing, just explaining you how to read the graphs, how to understand the graphs. Therefore, the area on the negative side of the force axis has a negative sign. Okay, so that's how we calculate the work done by the two forces. Okay, so work done by F, capital F is equal to plus 1750 joules. Okay, and work done by small f is minus 1000 joules. Therefore, total work done is equal to 1750 minus 1000, which is equal to 750 joules. Okay, so that's how you can solve this question. Okay, so that thing being said, that is the end of your discussion regarding initial understanding of the concept of how we can apply differential calculus into your work to be done. Okay, so let me stop it here only. I will just do a quick revision. So I won't start a new subtopic right now. We'll start this next subtopic in the next lecture discussion, in which we will understand how will we apply this. How will we apply the work energy theorem into this variable force? So how we will say that, okay, so now the force is not constant. Now this force is again a variable, and how, if this force is variable, we can apply the concept in the work energy theorem. Please recall work energy theorem. Work energy theorem was simply if the change in kinetic energy is equal to the change in work done, or basically the work done. So we will understand that in the further classes. So I will just do a quick revision so that we are intact. We can understand each and every concept which are coming forward. So we start with the scalar product first of all. So scalar product is basically nothing but A dot B, which is equal to AB cos theta. Then second thing which you understood is that AX BX plus AY BY plus AZ BZ is nothing but equal to A dot B. Correct? Then understood kinetic energy theorem, that is change in kinetic energy is nothing but equal to work done, or we can write it as half of mv square minus half of mu square is equal to F dot D. Correct? Moreover, what else we can write? So next thing which we got was kinetic energy. Kinetic energy is nothing but equal to half m v dot v, which is written as half m v square. Then we got to know about force also, the work done also. The work done is nothing but equal to F dot D, which is nothing but equal to F D cos theta. So there can be three instances when this work done can be equal to 0. So either the value of D is 0, or the value of F is 0, or this theta is at 90 degrees. Okay. Then finally, we understood the work done by variable force. So when we need to understand the work done by variable force, if we take the value of delta x to be very, very 0, so then we can say that W is nothing but equal to summation xi to xf. Understand this is equal to nothing but f of x into delta x. Okay, and if we say that delta x tends to 0 for that limit, what we can say that this work done is nothing but equal to integral xi to xl f of x dx. Okay. So how can this thing be explained? This can be understood like this, that let us suppose that there is some x, this is some force f of x, and if there is movement like this, let us say, then if we are starting from this location, we are reaching this location, so the work done is nothing but the area under this curve. Okay, so that thing being said, let me stop this discussion here only. We'll start with this work energy theorem for variable force in the next part of this lecture. So the course progress for you, we have completed with the introduction, then the notions of work and kinetic energy, work energy theorem, then work is done, kinetic energy is done, and work done by the variable force is also done. In the next part of this lecture, we'll start with the work energy theorem for a variable force and then move forward. Fine. That thing being said, let me stop the discussion here. So, thank you so much.